We're now going to talk about what the gradient of a scalar field means physically by looking at the physical picture. The gradient of a scalar field is a vector that describes the change in the field at each position. And how can we see this? If we take the dot product with an incremental displacement dr of the gradient of a scalar field, gradient of phi, this is going to give us, using the subscript summation notation, dr is dxi ei hat, the dot product with the gradient vector, let's point in ej hat direction, the derivative of the scalar field phi with respect to xj. So that's using the subscript summation notation, how we can represent the dot product with a small displacement. Now, because this is a dot product, that this implies delta ij, so that means we will have d phi del xi dxi. So let's see here. The dot product with a incremental displacement dr of the gradient of this function phi, scalar field phi, is equal to del phi del xi dxi. So if we go back here, we had dxi here, I hat dot ej hat is delta ij, so this becomes delta xi, therefore we have del phi del xi dxi. And what is this? We're taking the partial derivative with respect to xi, multiplying it by small changes in xi. This gives us the change in the scalar field phi at that point. So this is going to give us d phi. All right. And what happens if the displacement, our incremental displacement, is perpendicular to the gradient? Then this means d phi, because the dot product will give us cosine 90, which is 0. D phi is 0. That means phi is a constant. Okay, so if we go perpendicular to the gradient, we find the phi is equal to constant surfaces. So we find that the gradient always points perpendicular to constant phi surfaces. So constant scalar field surfaces. So that this is an important finding. The physical meaning of the gradient is it's always pointing perpendicular to constant phi surfaces. As an example, let's consider the scalar field phi of xy is equal to minus xy. What is the gradient of phi? It's del phi del x, del phi del x ex hat, plus del phi del y ey hat. So that's the gradient of this scalar field. So because phi of xy is minus xy, if we take a partial derivative with respect to x, this will give us minus y. So this is minus y ex hat. And the partial derivative with respect to y will give us a minus x. So this is going to be minus x ey hat. That's the gradient. Now let's plot this function. Phi is equal to a constant surfaces and the gradient of this scalar field, which is this vector field. And at point 1, 2, x equals 1, y equals 2, move to the right by an infinitesimal amount dr in plus x direction. And then we will calculate the change in the function d phi. This is gradient of the scalar field, gradient of phi dot product with the incremental displacement dr. And our gradient we have calculated to be minus y ex hat and minus y x e y hat. Now x is equal to 1, y is equal to 2, so we have minus 2 ex hat, y is equal to 2, x equals to 1, minus 1 ey hat, and we're taking the dot product with a small displacement in ex hat direction. So this gives us, as you can see, minus 2 dr. Okay, so what does that mean? This means that the phi of xy, because we have found minus 2 dr, is going to decreases by 2 units for every unit moved in positive x direction. Okay, on the other hand, if you look at it at point 34, if our displacement is 45 degrees to the x direction, which is dr over square root 2 ex hat plus ey hat, which means we are moving 45 degrees with respect to the positive x direction, then we can calculate the change in our scalar field, gradient of phi dot product with the displacement dr. So this gives us now at point 34, so x is equal to 3, y is equal to 4, y is equal to 4 minus 4 ex hat, and then minus 3 ey hat. We have evaluated the gradient at 3, 4, and then take the dot product with dr divided by square root 2 ex hat plus ey hat, and this will give us minus 7 divided by square root 2 dr. Okay, so that's for another point. We have looked at the change in the function in a certain direction. Okay, if instead we talk about the change in the function for a finite path, we need to integrate this. So if not at a point but along a finite path, what is the change in the function delta phi? This is going to be the path integral over the path L, the small displacement dr dot product with gradient of phi. So if we go along a certain path, this will tell us how much the function changes on that path. So on path L. So for each point, we take the dot product of the displacement with gradient of phi. That tells us the change in the phi function in the vicinity of that point. And if we go on a certain path, then we can calculate the change in the function also following that path. For example, if phi is equal to minus xy is an electric potential, then the electric field is related to the electric potential as minus the gradient of the electric potential minus gradient of phi. Now, we can evaluate this. This is minus xy is the potential, so minus minus plus partial derivative gives us y ex hat, and then partial derivative with respect to y gives us x ey hat for the electric field. So what I have done here is I've taken the partial derivative of the scalar field phi, which is my electric potential, with respect to x ex hat, and then minus the partial derivative of phi with respect to y ey hat. So that's how I calculate the electric field. And what does it say? It says that electric field's y component is equal to x and electric field's x component is equal to y, such that at each point in space, y component of the electric field divided by x component of the electric field is x over y. Okay, so this means the field lines follow the function dy dx is equal to x over y. So that's the function they will follow, which means integral of y dy is equal to integral of x dx. So we find y squared over 2 is equal to x squared over 2 plus a constant c, or we can write y squared is equal to x squared plus another constant c prime. So the function that we obtain is x squared minus y squared is equal to a constant which describes a hyperbola. Okay, so here I have recalled the constant c prime minus c prime as a constant c, for example. Okay, so if we plot this, that's basically what we're going to see. These are the electric field lines, and the density of the field lines increases. This is our convention as we move away from the origin, and the electric field lines are perpendicular to pi is equal to constant surfaces. So that's what we know from our analysis of the gradient. Okay, so this function phi is equal to minus xy, I can plot it using a contour plot in Mathematica between minus 5 and 5, x equals minus 5 and 5, and y is equal to minus 5 and 5. And also I can plot my electric field lines by taking minus the gradient of this function and doing a vector plot. And doing so, I obtain the constant electric potential surfaces like this. So that's my plot, where the color indicates the magnitude for this function, and we can see that it increases as I go down here, and it decreases as I go in this direction. Now, electric field lines are always perpendicular to these constant phi surfaces, as you can see in this plot, and they're pointing in minus the gradient direction. And also, the strength of the electric field is shown with this color scale here. So we have a higher strength, for example, at these points here, and then we have lower strength closer to the center. So this matches with what I have drawn here. The intensity decreases, so the field line's density is going to be a lot less as we move towards the origin, and the density increases as we go far away, and actually it becomes really high at these edges here. So you can see that these red ones are going to correspond to that. So in this mathematical plot, we use not the density of the field lines, but the color scale in order to indicate the change in the strength of the electric field or the electric field magnitude. Okay, so now we have discussed the physical meaning of the gradient of a scalar field. We can understand its meaning by looking at the dot product with a small displacement at a certain point, and we see that that gives us the change in that function, scalar function, for a small displacement about a certain point. If that small displacement is perpendicular to the gradient, the change in the function is 0. In other words, the gradient of a function always points perpendicular to constant phi surfaces, and we have shown it with one example, the function scalar field being minus xy, and when we plot the phi is equal to constant surfaces at point, for example, 1, 2, if we move to the right, plot by an amount plus dr in x plus x direction, this gives us a decrease in the function at by an amount minus 2 dr. And if we do it, so x equals 1, y equals to 2, if we can actually show it here, x equals 1, y is equal to 2, that would be here, right? So if we move away from the function around about that point in the x direction, the function decreases. So you can see that the scalar value decreases here if I go for a small amount in plus x direction. That's what we see. And we have also looked at the gradient of the electric field around that point, and that's basically what we have done here. And you can see that the gradient of the minus the gradient of the function, which is the electric field corresponding to this potential, always points perpendicular to the constant phi surfaces. Okay, and if we try different points, for example, and we can move in different directions, and we can calculate the change in the scalar function that way. And if we go on a certain path, not look at the change in the function at a certain point, but along a certain path, then this turns into a path integral. And the functional behavior of the gradient we can basically find out using this relationship. The y component divided by the x component is x over y. So this tells us that this function, the gradient, basically follows a hyperbolic function. And normally in these plots we show the density as the indicator of the strength of the electric field. The strength of the electric field decreases as we go to the origin and increases as we go far away from the origin. And especially for large x and y values, we have a large density, which means a high electric field magnitude. Okay, but in Mathematica code here, we have shown the color scale in order to indicate the change in the magnitude of the electric field.